In this lecture, we are going to discuss about the steady state error based on the type of system. So let's see what we are going to cover here. So first we'll discuss about the steady state error for type 0 system. After that we'll discuss type 1 and then at the end we'll discuss type 2 system. So let's consider a transfer function of type 0 system. We can write it as g of s into h of s, and that will be equal to k bracket 1 plus t1 s bracket close. Then again we can write as 1 plus t2 s bracket close and so on, divided by 1 plus ta s, then 1 plus tb s, and so on. Now this transfer function represents a type 0 system. Why? Because we have already learned in previous lectures that in order to find the type of system, we need to see in the denominator that we are having any pole at the origin. So the number of poles at the origin determines the type of system. So how we can extract from this transfer function that whether we are having any pole at 0 or not? So if we are having any separate s in the denominator, that tell us that we are having pole at 0. But here we are not having any separate s. All the s term that we are having is with some constant. So here we are not having any separate s term. That means we are not having any pole at 0. So that indicates it is a type 0 system. Now how we can get this type of transfer function? Because what we know is transfer function is written as g of s into h of s is equal to s plus z1, s plus z2, and so on, divided by s plus p1, s plus p2, and so on. So here z indicates the zeros of the system and p indicates the pole of the system. So this one we have already discussed. So this factorized form we used in order to determine the type of system. So here, in order to convert this transfer function to this one, that is also called as a time constant form of a transfer function, what we need to do, we have to take z out from these brackets and p out from the denominator. So that we can do as we can take z common here, so z1 into z2 and so on. We will be having one bracket, and then we will be having, we can write it as 1 plus s by z1, because here we have taken z1 common from this bracket and z2 common from this bracket and so on. So here we will be having 1 plus s by z2 and so on, divided by, we have to take p out from all these brackets. So we'll be having another term as p1 into p2 and so on. Then we will be having these brackets as 1 plus s by p1, 1 plus s by p2, and so on. So here this z1 z2 another term divided by p1 into p2 and other term we can treat it as a constant. So we can write this one as k here in the numerator, and this term here 1 by z1 and 1 by z2 we can write in the form of t1 t2. So we will be having 1 plus t1 s, then we will be having 1 plus t2 s, and so on. And here in denominator we will be having 1 plus, now we will be considering here that 1 by p1 is ta, so we'll be writing ta s and 1 plus tb s and so on. So here t1 t2 represents 1 by z1, 1 by z2, and so on, and similarly ta and tb are representing 1 by p1 and 1 by p2 and so on. So we can convert the given transfer function into time constant form in this way. So now let's determine the steady state error here. So let's consider the type of input here first. So first we will be considering step input. So for step input, in order to find the steady state error, that is given by ESS is equal to A by 1 plus Kp, where Kp is positional error coefficient. So first we need to find Kp here, and then based on that we can determine what will be steady state error for type 0 system when we are applying step input. So in order to find Kp, we know that it is given by limit s tends to 0, then g of s into h of s. So now we are having g of s into h of s as a type 0 system. So now we will be substituting that here, and on that we are going to apply this limit. So we can write it as limit s tends to 0, and in place of g of s into h of s we will be writing type 0 system. So k 1 plus t1s 1 plus t2s and so on, divided by 1 plus tas 1 plus tbs and so on. So here so when we apply limit to this type 0 system, we will be having, since k is constant, it will come outside, and we will be having, so again in numerator 1 is constant, so we will be having 1 as it is, then plus limit s tends to 0 t1 of s, then same we will be having 1 plus limit s tends to 0 t2 of s and so on. Same way in the denominator also we will be applying limit. So we will be having 1 as it is plus limit s tends to 0 ta of s, 1 plus limit s tends to 0 tb of s and so on. So here we are having constant and s, and that s tends to 0, so this term will become 0, and similarly this term will also become 0, and here in denominator also we will be having these term as 0. So we will be left with only 1 from each bracket. So we will be having k into 1 into 1 and so on, divided by, again here we will be only left with 1 into 1 and so on. So it is nothing but k only. So here kp we got as k. So now let's find the steady state error here. So ess will be equal to a by 1 plus k. So this is the steady state error when we are having type 0 system and we are applying a step input to it. So we can see that this error is finite, and that too it is a constant value. The same way we can find for other type of input considering this same type 0 system. So let's do that. So we'll consider now ramp input. So for ramp input, we know that steady state error is given by a by kv. So kv is what? It is a velocity error coefficient. So we have to first find value of kv. So let's do that. So let's do it here. So kv is equal to limit s tends to 0, and it is s into g of s into h of s. So now we are having value of g of s into h of s, that is this type 0 system, and we'll substitute it here. So it will be limit s tends to 0 s into k into 1 plus t1 of s, 1 plus t2 of s and so on, divided by 1 plus ta of s, 1 plus tb of s and so on. So here we know that when we are going to take a limit to this term, it will going to give us 1 only, and k will be constant, but here we are having a s term separate, and we know that that value is going to 0. So here this entire term will become 0. So here we will be having this value as 0. So velocity error coefficient for type 0 system when we are considering a ramp input is 0. So now let's find the steady state error. So it will be a by kv, and we are having kv as 0. So steady state error will be infinity here. Now same way we can find for a parabolic input also. So let's do that. That will do here because of the space constraint. So let's consider the third one, that is the parabolic input. So whenever we are having parabolic input, we know that steady state error is given by a by ka, where ka is acceleration error coefficient. So first we need to find that. So ka we know it is given by limit s tends to 0 s square into g of s into h of s. So here we know this value, we have to substitute that. So it will be limit s tends to 0, we will be having s square into k in bracket 1 plus t1 s and 1 plus t2 s and so on, divided by, we will be having 1 plus tas, 1 plus tbs and so on. Now here, irrespective of this term, when we are going to substitute the s value to be 0, so here we are having s separately, so because of this one we will be having entire value 0. So here also ka will be 0. So now when we find the steady state error, it will become a by 0. So again it will be a infinity. So this means whenever we are having type 0 system and we are using a parabolic input, steady state error will go to infinity. So in this way we can determine the steady state error for a type 0 system based on various input. Now let's find the steady state error for a type 1 system. So again, for a type 1 system, we can have the transfer function as g of s into h of s. So it will be k 1 plus t1s 1 plus t2s and so on divided by s into 1 plus tas 1 plus tbs and so on. So now this one is the transfer function for type 1 system, because we are having a separate s that indicates we are having one pole at the origin. So if we are having one pole at the origin, that indicates it is a type 1 system. So now let's find the steady state error for this type 1 system when we are having input as step input. So for step input, we know that steady state error is a by 1 plus kp. So again, this steady state error depends on here the value of transfer function. So let's find that kp. So kp, we know that it is given by limit s tends to 0. So in place of g of s into h of s, we'll be substituting this value. So it will be k 1 plus t1s 1 plus t2s and so on divided by s in bracket 1 plus tas and 1 plus tbs and so on. So now when we substitute the limit here, we know that when we substitute limit to this bracket, it is going to give us 1. But since here in the denominator we are having s, so when we substitute this value here, so it will become k by 0, and now it is going to give us infinity. So here we can see that positional error coefficient is infinity for step input when we are considering type 1 system. Now let's find the steady state error. So it will be equal to a by infinity. So whenever we are having anything divided by infinity, that is going to give us a 0 value. So we can see that for type 1 system, considering step input, we are having steady state error as 0. Now let's find the steady state error when we are considering a ramp input. So for ramp input, steady state error is given by a by kv, and kv, we know that how to find it is limit s tends to 0 s into g of s into h of s. So now we can substitute this transfer function value here. So it will be limit s tends to 0 s into k 1 plus t1s 1 plus t2s and so on divided by s 1 plus ta of s 1 plus tb of s and so on. So here we can see that this s and this s we can cancel. So now here when we substitute the limit, brackets will going to give us 1 and we are having a constant value here. So we will be having k here. So this indicates that kv is some constant value. So now let's substitute that here. So steady state error will be equal to a by k. So this indicates that steady state error for a ramp input when we are considering type 1 system is finite and constant. Now let's find for the parabolic input. So for parabolic input, we know that steady state error is given by a by ka, where ka is acceleration error coefficient, and we know that how to find it. So it will be limit s tends to 0, we will be having s square into g of s into h of s. So now let's substitute the value. So we will be having limit s tends to 0 s square into g of s into h of s is this value. So it will be k 1 plus t1s 1 plus t2s and so on divided by s 1 plus tas 1 plus tbs and so on. So again here we can see that 1s from denominator and 1s from numerator we can cancel. So we will be having limit s tends to 0 s into k 1 plus t1s 1 plus t2s and so on, divided by again same denominator. So now here again, if we substitute the limit, we know that because of this s, this entire value will go to 0. So here we are going to get a 0 value. So now let's substitute this one in a steady state error equation. So we will be having steady state error will be equal to a by 0, that is infinity. So for parabolic input, when we are considering type 1 system, we are going to get steady state error as infinity. So in this way, we can find the steady state error based on the type of system that we are having and under the given input. So now let's find the steady state error for a type 2 system and see how it changes with respect to type of input. So again, the transfer function for a type 2 system, we can write it as g of s into h of s, and that will be equal to k 1 plus t1s 1 plus t2s divided by s square 1 plus tas 1 plus tbs and so on. So here also we know that how this is the type 2 system, because we are having two poles at the origin, because here we are having, so we know that this is the transfer function for a type 2 system because we are having two separate s, and that indicates what, we are having two pole at the origin, and because of that it is called as a type 2 system. So let's find the steady state error considering first the step input. So for step input, the steady state error is given by a by 1 plus kp. So again we have to find kp here. So kp will be equal to limit s tends to 0 g of s into h of s. So now let's substitute this value. So limit s tends to 0, we will be having g of s into h of s as this value. So it will be k 1 plus t1 of s 1 plus t2 of s and so on, divided by s square 1 plus tas 1 plus tbs and so on. So here when we substitute this limit, so we will be having 1 for each bracket, but because of the separate s, we will be having 0 here in the denominator. So it is going to give us k by 0, and that is infinity. So again, when we substitute this infinity in place of kp here in this steady state error equation, so we will be having a by 1 plus infinity. So again 1 plus infinity is infinity and a by infinity is 0. So for this case, we are getting steady state error to be 0. Now let's find for the ramp input. So for a ramp input, we will be having steady state error as a by kv. So we need to find this velocity error coefficient, and that is given by limit s tends to 0 s into g of s into h of s. So let's substitute this value here. So we will be having limit s tends to 0 s into k into 1 plus t1s 1 plus t2s and so on, divided by s square 1 plus tas 1 plus tbs and so on. So here we can divide this numerator from this denominator, but still we will be having one separate s here. Now when we substitute the limit here, so each bracket will going to give us 1, but since we are having s here in the denominator, it will be 0 here, so we will be having k by 0, which is infinity. So if we substitute that value in the equation of steady state error, so it will be a by kv we got as infinity, so this value will be 0. Now let's find for a third case. So we'll be considering a parabolic input. So for that, steady state error is a by ka. So here ka we know how to find, it is limit s tends to 0 s square into g of s into h of s. So now let's substitute the value. So we will be having limit s tends to 0 s square into g of s into h of s. So in place of g of s into h of s, we need to substitute the transfer function value. So it will be k 1 plus t1s 1 plus T2s and so on divided by s square 1 plus TAS 1 plus TBS and so on. So here what we can do, we can divide this numerator, that is s square, from the numerator and s square from the denominator. So what we can do here, we can divide s square from numerator and denominator. So we will be having this sum only. Now when we substitute s to be 0, here we know that each bracket will going to contribute 1. So we will be having k into 1, so it will be k. So here we got Ka as some constant. So based on this one, we can determine the steady state error. So it will be A by K. So here we can see that when we are having type 0 system and we are applying parabolic input, so the steady state error is finite and that to a constant value. So in this way, we can determine the steady state error for any type of system considering a given input. So let's summarize what we have studied in this lecture. So let's consider for a type 0 system. So for a type 0 system, we got positional error coefficient as K, velocity error coefficient we got as 0, and acceleration error coefficient we got as 0. And the steady state error for a step input we got as A by 1 plus K, which is a constant. For a ramp input, we got it to be infinity. And for parabolic input, we got as infinity. For a type 1 system, we got positional error coefficient as infinity, velocity error coefficient as constant, and acceleration error coefficient as 0. Now the steady state error, when we consider step input, we got as 0. For a ramp input, we got it as A by K, and for parabolic input, we got it as infinity. For a type 2 system, positional error coefficient we got as infinity, velocity error coefficient we got as infinity, and acceleration error coefficient we got as constant. So for a steady state error, when we have considered step input, we got it as 0. For ramp input, we got it as 0. And for parabolic input, we got as A by K, which is a constant term. So in this way, we can determine the steady state error for a given system